What's up, Raiders? So I just want to do a sample level 1 pulley problem for you here, and then in the future videos we can take a look at level 2 or level 3 pulley problems. All right, so level 1 pulley problem is basically where you have two boxes hanging freely above the ground and just held back by the tension in the rope from the weight of on the other side. So let's say the box on the left has a mass of 5 kilograms and the box on the right has a mass of 7 kilograms. So there's really a variety of questions I could ask you here, but pretty typical things that I would ask is something about the motion of this system. So I might ask something like, if I give you a little piece of extra information, if I say something like, if the heavy box is 5 meters above the ground, how much time will it take to reach the ground? And then another question I could ask here is, what is the tension in the rope? Because hand in hand with that, you can figure out if the rope can actually handle it. For example, if your calculated tension in the rope was 58 newtons and the rope had a tensile strength of 60 newtons, well, 58 newtons of actual tension's a little below that 60 newton rated value, it'd be okay. But if the tensile strength that was rated at was 60 newtons and your calculated tension from your system was 62 newtons, then the rope would break. Okay, so with any pulley problem, whether it's level 1, level 2, or level 3, the overall steps to solving it are the same. The first thing you do is identify the direction your system's going to move. So obviously it's going to go in the overall direction of the heavier one. So we're going to identify the direction of motion, and we're going to make that direction positive. Then the next step is to draw free body diagrams showing the forces acting on each of the hanging masses. So we'll do the 5 kilogram block here. So the force of gravity or the force of weight, those terms mean the same thing. The bottom line is, what effect does gravity have on that mass? So it's mass times gravity. So 5 times 9.8. So the force of gravity acting on the 5 kilogram block, or its weight, is 49 newtons. And it has a tension force from the rope being attached to the weight on the other end that tends to pull it up. And remember, we said that we're going to make the direction of motion positive. So for the 5 kilogram block, I'm going to just draw a little reminder on the side for myself. This is not formally part of the free body diagram. This is the free body diagram showing all the forces that are acting. This little reminder here is just for myself to remind myself that, hey, this 5 kilogram block is moving up. So in a little bit, when I have an equation to analyze the motion of this box, anything up will be positive, anything down will be negative. Now I'm going to do the same thing for the other hanging box, the heavier one, the 7 kilogram box. Well, again, the force of gravity is trying to pull it down. That's what gives it weight. So you find it by mass times gravity. So 7 times 9.8. So the weight of the 7 kilogram box is 68.6 newtons, or the force of gravity means the same thing. And then what's keeping it from just plummeting to the ground in free fall is the tension in the rope from the weight on the other end. Now, an essential puzzle piece here that we're going to apply a little bit later is the fact that this system, these two boxes connected by the one rope, the tension is the same everywhere in the rope. So we don't know what the tension is pulling up in the 5 kilogram box or the tension pulling up the 7 kilogram box, but because they're both attached to the same rope, the tension is going to be the same everywhere. So the tension on the left side will equal the tension on the right side. We're not going to use that right now, but we will soon enough. So the next step now is applying the either-or test to any object we study from the motion perspective. Either the forces acting on it cancel out or they do not. Well, obviously we do not have equilibrium here. They're not the same, so they're unbalanced forces. So then we're going to have some acceleration. So that tells us instead of F net equals 0, like equilibrium, it's going to be F net equals ma. So we're going to apply that to each of these objects. So remember, net force just means the combined effect of all the forces acting in whatever direction or line of motion you're analyzing. So for the 5 kilogram block, it's moving vertically up, and both of these forces, the force of tension pulling it up and the force of weight trying to hold it down, they're both in a line of motion. So we're going to include both of those. The force of tension and the force of weight, those combine to make this 5 kilogram mass accelerate at some rate. We don't know what the acceleration rate is. That's what we're going to figure out. And notice here, I just identified the forces that are being combined for the net force. But force is a vector quantity. Direction matters. And we show direction with positive and negative signs. So here's where I'm going to rely on my little reminder note for myself. At the very beginning of the problem, we made the direction of motion positive. So for the 5 kilogram block, because it's lighter, it's moving up. So anything up for the 5 kilogram box is in the direction of motion. That'll be positive. Well, in this case, the force of tension is in the direction it's moving. So the force of tension, we don't know it, but it's going to be positive. But the force of weight is against the motion, so that's going to be negative. So it's Ft minus 49 equals 5A. And notice we have a little bit of an issue here. We have one equation, but we have two unknowns. We don't know force of tension, we don't know acceleration. So we're kind of stuck right now. All right, well, we'll circle back to that. Let's go to the other heavier box. Again, I'm going to identify the combined effect of the forces acting on it, F net. Well, it's the force of tension and the force of weight again. And those two forces combined will make this 7 kilogram mass accelerate. And again, a little reminder for myself about direction. We made the direction of motion positive. So the 7 kilogram box, since it's heavier, that's moving downward, so down is positive. So it might look like on the surface that we're being contradictory here. We're saying up is positive for the 5 kilogram block, but then down is positive for the 7 kilogram block. But we're really being consistent because the entire time, that's saying the direction of motion is positive. The 5 kilogram box is moving up, that's a positive direction, and then spinning around the wheel, continuing to follow the direction of motion, down is positive. So it looks like it might be contradictory there, but it's not. So let's go through and attach some signs now, because force is a vector quantity and direction matters. So the force of tension acting on the heavier block, it's holding it back from the way it's moving. It's against the motion, so that's negative Ft. And the force of weight, or the force of gravity, acting on this heavier box, that's in the direction it's moving, so that's positive. But notice we have the same problem that we did for the other one. We have one equation, but we have two unknowns because we don't know force of tension and we do not know the acceleration. So here's where we have to go back to that concept that we talked about at the start of the problem. The rope connecting both of these boxes together, collectively the rope is under a lot of tension because the weight hanging on each end. So we don't know what the tension is, but the tension's the same everywhere. So this force of tension on the left side is going to equal the force of tension on the right side. So that's a pretty critical piece for us here because we're going to be able to solve this as a system of equations. So we're going to take each of our equations here and we're going to rearrange them to get expressions for force of tension. So for this one here, I'm going to add 49 to both sides. So force of tension equals 5A plus 49. So we still can't solve it, but now we have an expression for the force of tension. We're going to do the same thing on the other side. Now notice, on the other side, we have negative Ft. So we can do this a couple ways, but I'm just going to add Ft to both sides so that I have a positive force of tension on the right side. And now to isolate that variable force of tension, I'll subtract 7A from both sides. So now we have a second expression for force of tension. So we still can't solve either of these equations. All we did was rearrange them, so we still have the same problem we have. One equation, two unknowns, one equation, two unknowns. But here's where we'll solve it as a system. We know the force of tension acting on the lighter box on the left is the same as the force of tension acting on the heavier box on the right. So the force of tension acting on the box on the left equals the force of tension for the box on the right. So now we can substitute our expressions for force of tension in there, see what effect that has. So 5A plus 49 equals 68.6 minus 7A. And notice by doing that substitution, now we have one equation, one unknown, so we can solve this. So I'm going to add 7A to both sides. 12A plus 49 equals 68.6. Subtract 49 from both sides. So 12A equals 19.6. Divide both sides by 12. And the acceleration then of our system, and against the system because both objects are attached to each other so they're moving as one, is approximately 1.63 meters per second squared. Now, it's always good to kind of reflect on your calculated acceleration here. This value should always be less than 9.8 meters per second squared. Because think about it, if either of these boxes were in free fall, where the only thing acting on it were gravity, they would be accelerating at 9.8 meters per second squared. So if I took scissors and I cut the rope, there'd no longer be any tension here. They would each plummet to the ground, accelerating at 9.8 meters per second squared. So no matter what, the lighter box, at least to an extent, holds the heavier box back at least a little bit from free fall. So no matter what, your calculated acceleration should always end up being less than 9.8. So now that we have that value, now we can kind of go the next step here and go back to our original question. If the heavy box is 5 meters above the ground, how much time will it take to reach the ground? So now we're going to analyze this as a one-dimensional motion problem like we did earlier in the year. And we go with the convention of up is positive, down is negative. Or to kind of cut out some negative signs, I can just say, hey, this whole thing is moving downward. I'm just going to make the direction of motion positive. So that's what I'm going to do. Now, there's a background assumption we have to make here, but it's a reasonable one. When this pulley system is being set up and the boxes are being secured to the ropes, it's reasonable to assume that it's not moving while you're setting it up. And then once it's all set up and you release it, then it starts to move. So based off of that reasonable assumption, the initial velocity in these pulley systems will always be 0. The acceleration, we didn't know it before, but we know it now. We just figured it out. It's about 1.63 meters per second squared. And we were told the box is 5 meters above the ground. So in terms of our equation variables, that's distance or displacement. Now, again, I'm choosing to make the direction of motion positive just because I like to eliminate some negative signs. So that's going to mean that this box is going to travel through a distance or be displaced 5 meters. So since I made the direction of motion positive and that was downward, both of these values are positive. If you chose to stick with the convention of up is positive, down is negative, no problem. These values would just both be negative, and then mathematically that ended up working out the same anyway. So we know these three values, and now from here, the question that was asked is how much time will it take to reach the ground? So we're trying to find t. So that specific combination of variables, if you look at your list of equations, sets up for the quadratic, d equals vit plus 1/2 at squared. So now just substitute your values in. Now the initial velocity is 0, so this term here is going to go away. So we have 5 equals 1/2 times the acceleration, or excuse me, approximately equal to, because the acceleration is approximate, 1/2 times that approximate acceleration rate of 1.63 times the unknown t squared. So now we have 5 is approximately equal to 0.815 t squared. Divide both sides by 0.815. So t squared is approximately equal to 6.13. Take the square root of both sides. So the time to the ground for that heavier box will be approximately 2.48 seconds. And then the last question that was asked, what's the force of tension in the rope? Well, we have multiple expressions for force of tension, and now that we know what acceleration is, we can just take either one of those and substitute our calculated acceleration in there. So I'll take the force of tension expression for the lighter box. That was 5a plus 49. Well, 5 times the unknown acceleration. Well, we know what it is now. So it's 5 times the approximate value of 1.63 plus 49. So that ends up being approximately 8.15 plus 49. So the force of tension is approximately 57.15 newtons. And then now you could just pay attention to the wording of the problem. If the question said something like the tensile strength of the rope was 55 newtons, this is too much tension, the rope would break. But if the tensile strength that was reported from the manufacturer of the rope was 60 newtons, you're okay, because that tension in the system is a little bit less than 60. So hopefully this helps. If you have any questions, like always, you can email me or send me a message in the Remind app. Take care.